Hi, everyone. This is the second part of Lecture 22, where we'll talk about the habitable zone. So, the basic question that we want to talk about today is, in general, what makes a planet suitable for life? And in particular, where in a system could a planet be suitable for life? Now, we only have one example of life in our universe, our own Earth. So, we have to be a little bit modest in whether we believe definitively whether or not our guesses are true, but we may as well take a stab based on what we know about life here on Earth. And one of the most important things, of course, for life here on Earth is water. Liquid water seems likely to be a really important characteristic or factor in terms of having the ability to have life on a planet. We are made mostly of water, and water facilitates the complex chemistry that life requires. So, where can liquid water exist in any system? This is the idea behind what we call the habitable zone. The idea is that in any planetary system, there's a region of that system that is very close to the star, and that's too close, where any planet will get heated up because it's so close in to the point where water will boil if there was any on the surface. That would not be in the habitable zone because we would not be able to sustain liquid water on the surface of a planet. There's a distance a little bit further out where it's a little bit cooler and water actually can remain liquid. And this is the distance where the Earth resides. This is the habitable zone. And we believe that Earth resides in the habitable zone of our own system. And then beyond Earth's orbit, back further away from the Earth where it's even cooler, it will just be too cold for any water to exist in liquid form. And all of that water will freeze and it will be outside of the habitable zone once again. So the idea is that we're looking for this very happy medium where it's not too hot for water and not too cold for water, but just right. And this is why it's often called the Goldilocks zone. So there are some cautions that I have to give. In particular, being in the habitable zone does not mean that a planet must have liquid water or can have liquid water right now. So, for example, there are other objects in the habitable zone of our own solar system, such as the moon and Mars. And as far as we know, neither of these two planets have liquid water on their surfaces. Perhaps Mars did in the past, but we don't see it there now. So just because there's a planet in the habitable zone does not necessarily mean that it is habitable at this very moment by that definition. And also, just because a planet or an object is outside the habitable zone does not mean that there's no liquid water. Take, for example, the moons of Jupiter and Saturn, like this image of Europa. Europa, we believe, has a liquid water ocean underneath its surface because it's warmed by tides from Jupiter. Europa is not in the habitable zone, but it's still probably one of the best places to look for life in our own solar system. So the habitable zone is by no means the end all and be all of habitability and whether there is life on a given location. It's just meant to be kind of a first general guess as to whether something is a promising place for life or not. So let's imagine for the time being that the habitable zone is a good place to look for life. So, how can we figure out where the habitable zone is for any given planet or any given system? One of the ways that we do this is by using climate models, very similar to the ones that we've developed on Earth, to map out the patterns and the habitability of a general system. So the idea is you have a planet that you simulate at different amounts, at different distances from any given star. You can change the amount of light that that planet receives based on how far away it is. And you run the climate model and you see in which ones there is able to be liquid water on the surface. If you start off a planet with liquid water, but very quickly all of that water turns to ice, that would not be in the habitable zone. Or vice versa, if you start off a planet with water, but it's close enough to the star that it's getting lots and lots of light from it, and all of that water very quickly evaporates and goes into the atmosphere, that would not be in the habitable zone. So you're looking for these climate models that retain this liquid water on the surface in order to define the habitable zone. In our solar system, this is what the habitable zone looks like. Interestingly, Earth is not the only planet that's in the habitable zone. Venus is very near the outer edge of the habitable zone, and Mars is within the habitable zone. We think that although these two planets don't look particularly hospitable to life like us right now, they could have in the past or could even today still have life on them. So it's not necessarily, 100% habitability or 0% habitability. Being in the habitable zone, as I said earlier, is not the end all and be all of whether there's life on the planet. Mercury is too far in. There are really no situations in which Mercury is cool enough to have liquid water on its surface. And further out, of course, is beyond where everything else is frozen in the system. So now let's think about what habitable zones might look like around different stars. We know that not all stars are like the sun. In fact, many stars are smaller, such as these red dwarfs that we call M stars down here. And many stars are much, much hotter and much, much larger than the sun. Our sun is kind of a middling, smaller star. And in the grand scheme of things, it's not particularly special in either way. So, is it possible for there to be habitable planets around small stars like these red dwarfs, or big stars like these blue giant stars? So, an important thing to know about stars is that the more mass a star has, the hotter and brighter it will be. Here's an image of two stars that are orbiting each other. This is called a binary star system. One of these stars has a mass that is similar to that of the sun, this bright one over here. This other one has a much smaller mass that's only about 20% the mass of the sun. You can see two things from this image. First of all, even though these stars are very close to each other, they're orbiting each other, and they're at the same distance, this one is much fainter than the more massive star. The reason for this is that this one is much less bright overall. The more massive a star, the brighter it is. The less massive a star, the fainter it is. The other thing to note about this is look at the color. This star has a bluish white color, indicating that it's relatively hot. Recall that the hotter an object is, the bluer the light it emits, and the cooler an object is, the redder the light it emits. This lower mass star is redder than its companion, and therefore it has this orangey color. So this star is both less bright and cooler, and therefore redder than its companion. This is generally the case. The more massive a star is, the hotter it will be. Similarly, the more massive a star is, the brighter that star will be. This graph is showing the brightness of stars as a function of their mass. So the way this affects the habitable zone is that the hotter, more massive, brighter stars will have a habitable zone that's further away from the star. This makes sense, right? If you're near a fire that's really, really bright, you may not want to be so close to it, otherwise it'll just be too hot. But if you're around a cooler, lower mass star, such as one of these red dwarfs, you want to huddle very close into that very dim star in order to be warm enough to have liquid water. So the less massive a star is, the cooler it is, the less bright it is, and the closer the habitable zone is to the star in order to have liquid water on the surface of a planet. The other thing to think about is how long do stars live? It may be a little bit counterintuitive, but it turns out that the more massive a star is, the faster it burns through its fuel. It's kind of like the old saying that someone who burns both ends of the candle will burn very brightly, but only for half as long. The exact same thing happens with stars. So the most massive, biggest stars, ones with almost 100 times or more the mass of the sun, only live for a few tens of thousands to hundreds of thousands of years. That's a blink of the eye on astronomical terms. Whereas our sun, which has a mass of only about a hundredth of these most massive stars, will last for about 10 billion years before its fuel runs out. And the smallest stars, the ones that are only about a tenth the mass of the sun, have lifetimes that will exceed 10 trillion years. It turns out that these stars will last so long that the age of the universe is not yet old enough for any of these stars to have ever run out of fuel. These stars will be continuing to burn fuel and continuing to do what they're doing for much, much longer than the universe has existed currently to date. In terms of life, this has important implications. We think that probably it took something between 100 million and a billion years for life to arise on our own planet. If we look for stars or if we look for life around stars that are more massive than, say, about 5 times the mass of the sun, those stars may just not live long enough for life to arise on any planets before they run out of fuel. So, in terms of looking for life in other solar systems, we may want to focus on stars with relatively low masses because those are the ones that are going to last long enough for life to arise before the star eventually runs out of fuel and no longer can warm the planets.